So today we're going to work another lesson in Unit 2. This is going to be lesson number 5, graphing techniques using what we call transformations. And this is going to be out of your book, section 3.5. So in this assignment, we're going to use transformation techniques and we're going to apply those to the parent functions. And we're going to generate these graphs of these new functions. So a lot of this can be done, like I said, on the calculator, but we're going to try to do this by just using 3 special points from the parent function and understanding the relationship of how the graph can be affected through transformations. The first type of transformation we want to deal with is what we call the vertical shift. A vertical shift is affecting the y values. And what this will do is this will shift the graph up or down. So if we have the parent function f of x, this constant, if it's a positive k, what that's going to do is it's going to shift our graph vertically. If we have our parent function f of x and we have this outside piece is a negative k, a negative constant, that's going to make the graph shift in a downward direction. So as we move into this lesson, we're going to be given this parent function, which is really the original form of everything. It's kind of what it starts out with. It's the most basic function. So we're going to use, to start with, f of x equals this x squared. Our goal, though, is to graph g of x, which is going to actually be f of x plus 2. Now, our parent function here is actually x squared. So we're actually going to be graphing x squared plus 2. So to do this, we're going to first start with graphing our parent function. So to graph our parent function, the square function, remember the square function, we need just 3 special points. And remember, it's that parabolic shape. It's a parabola. In other words, it's also what we call a U-shaped graph. So when I put a -1 in, that would give me a 1. If I put a 0 in, that would give me a 0. If I put a 1 in, that 1 squared would also be a 1. So we have those 3 ordered pairs. So when I graph my function, I'm going to do this in a light color. This is just going to be a reference. So I have this -1, 1, this 0, 0, and this 1, 1. And my graph is going to be this parabolic shape, and I'm just going to use a dotted line as a reference. So that's what the graph starts out as. Now, as we look at our new graph, notice how the parent function has this addition of a 2 next to it on the outside. This plus 2 is going to shift the graph vertically. This is going to make the graph move up 2. So what we're going to do is use these original order pairs over here. So we're talking about these original order pairs over here. And what we want to do is create a new table using those order pairs. So notice how the -1, the 0, and the 1, we've already kind of put those over here. Those have already been done for us. We have that -1, 0, and 1. They don't change. The x values don't change. What's going to change are our y values. So when that y value is a 1, we're now going to add a 2 to that. And that's going to give me my new y value of 3. My x value was a 0 over here. And now we're going to add a 2 to that. 0 plus 2 is going to give me this 2. Over here, we had this 1. We're going to add a 2 to that 1. And that's going to be my new y value, which is a 3. So my new ordered pairs are going to be this -1, 3, this 0, 2, and this 1, 3. So these are going to be the points I'm going to use to graph my new function. So -1, 3 would be here. 0, 2 would be here. And 1, 3 would be here. So notice how my original points have all been moved upward 2 spaces, a shift of 2. And so now I have my new parabola would be here. And it kind of goes across like so. So it's going to be my new graph would be that. Sorry, I don't have that nice graphing tool in Blackboard. Mine are going to be a little bit more handmade. So that's going to be what our goal is to use the parent function and use the transformation to create the new graph. So here's my new function, f of x equals x cubed. So this is my parent function. And our goal is to graph this function over here, g of x equals f of x minus 4. So in other words, the parent function, which is x cubed, we want to subtract 4 from it. Our goal, though, is to use the parent function to start with. So our goal is to graph this f of x to start with. So I'm going to make a little table here. So I have a -1, and if I put -1 in, -1 cubed would be -1. 0, 0 cubed would be 0. 1, 1 cubed would be 1. So I'm going to graph those 3 ordered pairs. So I have a -1, -1, and I'm going to do that in a lighter color. Let's do that. -1, -1 would be there. 0, 0, and 1, 1. Now remember, the cube function is snake-like. So it's going to kind of come down along the y-axis. It's going to cut across the origin and then turn around and go across along the y-axis from the other side. So that's the snake function. It kind of makes that look. So our new function, we want to graph. Notice how we have this -4 on the outside. That -4 means we're going to have a vertical shift, but it's going to be going down 4. So again, the x values are not changing. The -1, the 0, and the 1 are not changing. But the y values, they're all being shifted by going down 4. So the -1, we lose 4. That gives me a -5. The 0, we lose 4. That gives me a -4. The 1, lose 4, would give me a -3. So my new order pairs would be -1, -5, 0, -4, and 1, -3. So my new order pairs, I'm going to graph those. -1, -5, 0, -4, and 1, -3. And remember, the graph is going to be a snake, so it's going to run along the y-axis. It's going to come down and cross through those points, and then it's going to run along the y-axis on the other side. So it's going to kind of take on that look there. So notice how those 3 points have all been shifted down 3. Each one of those points has been shifted down, down 4. So down 4, down 4. And that creates our new function, our new graph. So the next type of vertical transformation is what's called a vertical stretch. A vertical stretch is when we multiply the outside of the function by a factor of a. So when you multiply on the outside, this is again going to affect the y values. Now the thing is, if a is between 0 and 1, in other words, if it's a small fraction or a decimal, what this is going to do, it's actually going to make the graph wider. This is called a compression, a vertical compression. If a is greater than 1, that's going to stretch the graph vertically. This is going to make the graph narrower. So as we move forward, we may see either a stretch or a compression based on that. So stretch is going to move the points further away from the x-axis, and the compression is going to move the points closer to the x-axis. Because remember, that's the y direction with respect to the x-axis. So if I look at the parent function f of x equals the cube root of x, and we want to graph then g of x is going to be this 2 times f of x. Again, we're going to graph this based on our knowledge of the parent function. So the order pairs were -1, -1, 0, 0, and 1, 1, if you recall. So we have the -1, -1. Again, I want to do that in a lighter color. So this -1, -1, this 0, 0, and this 1, 1. Now remember, the cube root of x, the cube root function runs closer to the x-axis. Runs along the x-axis and it turns and crosses and runs along the x-axis from the other side. So that's the cube root function as it takes on that look. Now what we want to graph is we want to graph 2 times f of x. So we want to multiply the outside by 2. what that's going to do is create a vertical stretch. So all we have to do again is keep the x values the same, the -1, the 0, and the 1, but all the y values are going to be multiplied by a factor of 2. So -1 times, so I'm going to multiply the 2 times the -1, which is going to give me a -2. I'm going to multiply 2 times 0, which is still going to be 0. And I'm going to have 2 times 1, which is still going to be this 2. So that's going to be my new ordered pairs. So the -1, -2 would be a point, 0, 0, and then 1, 2 becomes a point. So those would be my ordered pairs. -1, -2, 0, 0, and 1, 2. So if we graph those, notice that those points got further away from the x-axis. So we call that a vertical stretch. And so when I draw it again, it runs along the x-axis, it turns and runs along underneath the x-axis as well. So that would be what we call the cube root function. It takes on that look. So notice how the graph has kind of been pulled further away. So the graph actually takes on that look. So our next parent function we want to deal with is this absolute value of x. So we want to graph that. But our ultimate goal is to graph this g of x function over here. Notice how I have this 1/2 in front of it now, 1/2 f of x. So to graph g of x, though, we have to know what the graph of absolute value of x looks like. Remember, that one is V-shaped. So when I graph this, it's going to take on a V. So again, I'm going to create the table of the 3 ordered pairs. Remember, absolute value is how far a number is from 0. So the absolute value of -1 would be 1. The absolute value of 0 would just be 0. And the absolute value of 1 would be 1. So I'd be graphing those 3 ordered pairs. Again, I'm going to do those in a lighter color. So -1, 1, 0, 0, and 1, 1. And this graph takes on a V-shaped graph. So it kind of shoots off in that direction, and it shoots off in this direction here. Takes on that look. So now what I want to do is I want to graph g of x, which is going to be this 1/2 times the absolute value of x. That's going to be the function I'm actually going to graph. So notice now we're going to be multiplying by this 1/2. That's actually going to make the graph get closer to the x-axis. So we call that a vertical compression. So when I multiply the y values by 1/2, that's going to be 1/2 times 1, which is just going to be 1/2. I'm going to multiply 1/2 times 0, which is going to be 0. And I'm going to multiply 1/2 times 1 again, which is going to be 1/2. So it's going to be my 3 new ordered pairs: -1, 1/2, 0, 0, and 1, 1/2. So if I graph those points, -1, 1/2, notice how it gets closer to the y-axis. That's a compression. 0, 0, and 1, 1/2 this way. So the graph does get a little wider as well, as you can kind of see. So the graph kind of takes on this little wider V-shaped graph. So that would be the graph of that function. So the next thing with the vertical, we have what's called a vertical reflection. A vertical reflection is when there's going to be this negative in front of the function. And what's going to happen is the parent function is going to get reflected over the x-axis. In other words, the y values are going to be changing sign. So the parent function, again, we're going to look at as this square function. And our g of x function is going to be the opposite of that function. So it's going to be the opposite of x squared. That's our goal, is to graph that function. Again, we're going to use the parent function to do this. So again, I like to use -1, 0, and 1 as my x values. And when we square those, that turns into a 1, a 0, and a 1. So when I graph my parent function, we have -1, 1, 0, 0, and 1, 1. And remember, this is a parabola shape or a curve, a U shape. So it kind of curves down and curves back up and takes off in this direction. So our parabola takes on that look. Now to graph g of x, notice how there's this negative on the outside. That's going to reflect the graph over the x-axis. In other words, it's going to change the signs of my y values. So notice how my y value was a 1. Now it's going to turn into a negative 1. My y value was 0. Well, that stays 0. But the other one is also going to turn into a negative 1. So when I graph this function, we're going to have then this order pair negative 1, 0, 0, and 1, negative 1. So when I graph those points, negative 1, 0, 0, and 1, negative 1, notice how the graph was opening above the x-axis. Now it's going to be flipped over the x-axis or reflected over the x-axis. And this is now going to be my new graph, is it's going to now be opening in a downward direction. So I have that parabola graphed. That would be called a vertical reflection in the parent function. The next thing we get into is what's called horizontal shifts. And these things are going to be on the inside. Notice how we have this f of x plus h. So this plus h is on the inside. And we have this minus h over here. Now the thing about horizontal shifts is things are backwards. If it's a plus h, it actually is going to go to the left. If it's a minus h, that actually means the graph is going to go to the right. So with horizontal shifts, it actually affects the graph in a backwards concept. You have to kind of think backwards here. Let's see if I can get this lined up where I want it. So let's look at this function here. So our parent function is f of x equals the square root of x. So we have this function here. And what we want to do is graph g of x, where g of x equals f of x plus 2. Remember, f of x plus 2 means you have to replace x with that. So this goes on the inside. So x gets replaced with x plus 2. So this is the graph we're trying to graph, is this one. But again, we're going to do this by using a horizontal shift. So again, to do this, though, I need to remember what the parent function looks like, the square root of x. The square root of x, remember, is it's kind of a right side curve, or a right arm up, if you will. And again, I can't really choose x to be negative, so we're using 0, 1, and 4. Since those numbers I can easily take the square root of. So the square root of 0 would still be 0. The square root of 1 would be 1. And the square root of 4 would be 2. So when I graph those order pairs, I have then, and I'm going to again do this in a lighter color, 0, 0, 1, 1, and 4, 2. So this graph, as we said, it kind of opens off to the right. It's a right side curve. It kind of takes on that look. Now, notice how when we graph this new function, the plus 2 was on the inside, which means this actually goes backwards. It's actually going to shift to the left 2. So what actually happens here is now the x values are going to get affected. The y values are going to remain the same. So the y values are still going to be this 0, 1, and 2. But on the x values, I have to lose 2 on each one of those, since it's going to shift everything to the left 2. So this is going to be 0 minus 2, which is going to give me a negative 2. I'm going to have 1 minus 2, which is going to give me a negative 1. And I'm going to have a 4 minus 2, which is going to give me a 2. So my new order pairs will be negative 2, 0, negative 1, 1, and 2, 2. So if I graph those points, negative 2, 0, negative 1, 1, and 2, 2, this would be, my graph would be over here, taking on that same little curve, going off in that direction. So notice how each one of those points has been shifted to the left 2. That's called a horizontal shift. Because again, a horizontal shift is going to be affecting the x values. So this is going to be more of a left and right concept. So if we look at this next function, we have what's called the reciprocal function, 1 over x. So what I want to do is I want to graph this guy over here, g of x, which equals f of x minus 3. So notice how, again, that x minus 3 has to go in place of x. So my new function is actually 1 over x minus 3. So when I graph this, we're going to use a different concept here. Remember, with the reciprocal function, we cannot involve the y-axis, so x cannot equal 0. We cannot involve the x-axis, y cannot equal 0. So the first thing we picked up on is we have these boundaries that are going on here. So the boundaries we have are the y-axis is a boundary, so we draw like a little dotted line here to say, hey, this graph cannot cross this broken line. The x-axis is also a boundary that it can't cross. So we have to draw those little boundaries in first. And when I graph the problem, remember, the reciprocal function says to take the reciprocal of 1/2, which would be 2. If I take the reciprocal of 1, it would still be 1. If I take the reciprocal of 2, that's going to turn into a 1/2. So when I graph this, I have this 1/2, 2, 1, 1, and I have this 2, 1/2. So remember, it's kind of slightly curved. So it kind of makes this look over here in the first quadrant. And remember, this is all mirrored off into the third quadrant. So everything gets reflected over. So I have this -1, -1, this -2, -1/2, and this -1/2, -2. Those 3 points get reflected across the origin. And by using symmetry, I can create the other half of the graph. So that's where that origin symmetry comes in and just reflect those guys over. So we have that kind of going on there where this point kind of gets reflected down here. The 1, 1 gets reflected to -1, -1, and the 2, 1/2 gets reflected into -2, -1/2. So we have that going on. So now what happens is we have this vertical shift. And again, I really should have did that in light colors. Let me try that again. Let's get rid of that. So we really wanted to do that in light. That's not our final graph. So we have this curve going through here, going through there like that. And then we have this other one going over here like that. So those are where the graph was. But now we have this f of x minus 3. Notice this -3 is inside the function. So that -3 actually tells me to go backwards, which means instead of going left 3, I actually have to go right 3. So that means I have to actually add 3 to the x values. My y values all stay the same. So this 2, this 1, and this 1/2 all stay the same. But what I'm doing is adding a 3 to the half, which gives me 3 1/2. I'm adding a 3 to the 1, which is going to give me a 4. And the 2, I'm adding a 3 to that, and that's giving me a 5. So those are my new order pairs. 3 1/2, 2, 4, 1, and 5, 1/2. Now, something else that we have to pay attention to is we were approaching the y-axis, but that vertical boundary has to also shift over 3. So that boundary is now shifted over here to where x equals 3. So this is my new boundary here, is that's actually shifted to the right as well, 3. So when I graph this, that's going to be important. So my first point I have is this 3 1/2, 2. So 3 1/2, 2 would be here. 4, 1 would be here. And 5 1/2 would be there. So my new graph is now takes on this look here. It kind of, let me try to do that a little bit better. This little pen just gets away from me sometimes. So try that again. So again, we're trying to make this slightly curved U in this spot here. So we have this graph here, and then this is all reflected across the origin. So we have these points here. So those are all reflected across there, and we have our little U over here on this side as well. So we just kind of use that symmetry to kind of create the other side of the graph, origin symmetry. So that creates our new function shifted over. So it's the reciprocal function just shifted over right 3. The next thing we have is what's called a horizontal stretch or compression. Notice this time the A is on the inside. So what's tricky is it's all backwards. So if A is a fraction, like 1/2, we actually have to use the reciprocal of it, and we multiply the x values by that. If A is greater than 1, say if A was 2, then we actually divide the x values by that value of A. So if I look at the function f of x equals x squared, let me get a little bit more down. So if we have this function f of x equals x squared, this is our parent function. Our goal is to graph g of x, which equals f of 2 of x. Notice that the 2 of x is on the inside. So that means we replace x with that 2x. So we end up with this function g of x equals 2x squared. So when we graph x squared, remember this is a parabola. So again, I like to use the -1, the 0, and the 1 as my x values. I would get a 1, a 0, and a 1 for my y values. So when I sketch my parabola, I have this -1, 1, this 0, 0, and this 1, 1. So again, I'm going to just try to use a dotted line, make a sketch of it. Now, notice how we have this 2 as a coefficient of x. But since it's on the inside, that actually means to divide by that value. So my y values stay the same, 1, 0, 1. So since you're multiplying by 2 and you have to divide by 2, notice your x values are going to be getting closer to the y-axis. So we'd have a compression in that sense of getting closer to the y-axis there. That would be a horizontal compression. So notice how things are backwards when you talk about x's. So that -1, we'd be dividing it by 2, and that would give me this -1/2. 0 divided by 2 would still just be 0. And 1 divided by 2 would just be this 1/2. So my new order pairs are this -1/2, 1, 0, 0, and we have this 1/2, 1 again. So -1/2, 1 would be here. 0, 0 stays there. And we would have 1/2, 1. So the graph looks kind of like that. So notice how this graph is much tighter with respect to the y-axis. So it's kind of been horizontally compressed, pushed closer. So you could say it's horizontally compressed, but you can also say it's been vertically stretched. It's narrow, depending which way you want to look at it. But since we're affecting the x's, we're really referring to more of a horizontal compression because of that. We also have what's called a horizontal reflection. Notice how the negative will be inside the parentheses. So this graph is actually going to reflect over the y-axis. In other words, the x values will have to change. So let's see if we can create this graph here. Move this all down. I think my graph is down here somewhere. There we go. That looks like we got everything together now. So again, we want to graph the square root function as my parent function, but our goal is to graph g of x, which is going to be f of -x. And what this means to do is replace x with the -x. So our new function is going to be g of the square root of -x, or the opposite of x. So when I graph it, remember with square root, we just use 0, 1, and 4. So the square root of 0 was 0, the square root of 1 was 1, and the square root of 4 was a 2. So when I graph this, we have 0, 0, 1, 1, 4, 2. And remember, the square root function is kind of a right side curve. It kind of curves closer along to the x-axis. Now, what we're doing is we're putting a negative inside. So that's going to be a reflection. And this is going to reflect over the y-axis. because the x values are changing. So when I write my order pairs over here, again, the y values are not changing. So I still have this a 0, this 1, and this 2, but all the x values are changing sign. So the 0 doesn't change sign, but the 1 turns into a -1, and the 4 turns into a -4. So if I graph these, we have 0, 0, -1, 1, and -4, 2. So notice this graph actually turns and opens up into a left curve, a left side curve. It opens on the other side of the y-axis. So that's what we mean by reflecting the graph over the y-axis. So again, the blue graph is not really there. It's just a reference to where we started at. So putting this all together, in this part, we're going to try to put the vertical and the horizontal transformations all together. And so let's look at this first question. If given y equals the absolute value of x, what they're asking us for is what's the new function if the graph has these following things. So A says, what's the new function if the graph is shifted to the right 4 units? Remember, the right affects is kind of an inside concept. That affects the x's. So the right kind of means we're inside. Remember, inside is backwards. So when I write my function f of x, it's going to be the absolute value of x. And since it says go right, I actually got to put a -4 here, because a -4 actually means to go to the right. It's always backwards. So that would be the function they're looking for. Reflected across the x-axis, that is going to be involving the y's. So it's going to be a reflection of the y's. So in other words, this is going to change the values of this is going to be when I write the function to reflect over the x-axis, the negative's got to be on the outside of the function, because that's going to affect the y's. So that's going to be then the opposite of the absolute value of x. Since this is a reflection that involves changing the y values, we're changing the y values, the negative's got to be on the outside. So vertically stretched by a factor of 5. And also, again, vertically means we have to be putting stuff on the outside. So that factor 5 has to be placed on the outside of the function. So f of x is going to equal 5 times the absolute value of x. So horizontally compressed by a factor of 4, notice horizontally means we have to do inside. But inside is always backwards. So if I give you this 1/4, we have to use its reciprocal. So f of x is actually going to equal, the reciprocal of 1/4 would be then 4x. And so that would be a compression of a factor of 1/4, because you would actually be dividing by 4. So the next thing they want us to do is we want to graph f of x equals 2 times x plus 1 squared minus 3. To graph this function, we have to first recognize the parent function. So the parent function is going to be this x squared function. So from there, remember, if I'm graphing the parent function, the order pairs I use again is a -1, a 0, and a 1. And that would give me a 1, a 0, and a 1. So when I graph the parent function, we have this -1, 1, we have this 0, 0, and we have this 1, 1. And it's going to be this parabola, the U-shaped graph. So the graph's going to take on that look. Now, to create my new function, what affects the x's would be the inside. So this +1 is going to affect the x's. So that means I have to lose 1 on my x's. So I have a -1, take away 1, that's going to be a -2. 0, take away 1, that's going to be a -1. 1 take away 1 would be 0. Now my y values, notice that there's two things affecting my y's. So my y values, notice how we have this we have this 2 out here, and we also have this -3. So there's two things happening to the y's. We're stretching them and shifting them. And remember, the y's are going to follow what we call the order of operations. So what I got to do then to the y's is I actually got to multiply the y's by 2 and then subtract a 3 to create the y values. So when I do that, I'm going to have 2 times 1 minus 3. That's going to be 2 minus 3, which would be -1. So -2, -1 would be a new point to plot. Y was 0, so 2 times 0 minus 3 is going to equal 0 minus 3. That's going to equal then a -3. So -1, -3 would be another order pair. And then the last one was 1. So again, it's 2 times 1 minus 3. That's 2 minus 3, which equals -1. So 0, -1 would be another point. So when I graph this, it should look like a parabola, but it's now going to be stretched vertically and moved as well. So I have this -2, -1 would be one of the solutions I see. -1, -3, -1, -3, and 0, -1. So notice how my graph has been moved from the origin, and notice how the y values are further apart because of that vertical stretch. So my graph should now kind of take on that look there, kind of a parabola shape, more curved, and kind of take on that look there. So that would be how we would graph that. So our next function we have is f of x equals the cube root of the opposite of x minus 2. So again, the first thing is identifying the parent function. Notice how the parent function is going to be this cube root of x. So when I graph that one, remember this is going to be the snake that runs along the x-axis. So again, if I use -1, 0, -1, we get -1, we get 0, and we get 1. So -1, -1, we'll do that again in a lighter color. -1, -1, 0, 0, and then actually, I didn't get the right y value there. That should have been an x value of 1. -1, 0, and 1 are my x values, and that does look right. So we have now this 1, 1 looks good. And this graph runs along the x-axis and turns and runs below the x-axis, kind of venturing further away, something like that. It takes that look there. My new function, if I look at what's going on here, on the inside, we have a negative on the inside. That means my x values are going to have to switch signs. That's going to be a reflection across the y-axis. So that -1 turns into a 1, 0 stays 0, but that other 1 turns into a -1. So the -1 turned into a 1, we have a 0, and then the 1 turned into a -1. On the y values, what we're seeing there is this -2s on the outside. So it's going to tell me that my y values are going to be shifted down 2. So I have to lose 2 on the y's. That's on the outside. So the -1, we have to lose 2, and that now gives me a -3. 0 lose 2 would give me a -2. 1 lose 2 would give me a -1. So my new order pairs would be 1, -3, 0, -2, and -1, -1. So 1, -3 would be here. 1, -3, 0, -2, and -1, -1. I did that again, didn't I? No, that's right. I just graphed something else wrong. Try that again. I went the wrong direction, didn't I? Y'all saw that, didn't you? Try to graph those 3 points again. So my first order pair is 1, -3. That means go right 1 and down 3. 0, -2, and -1, -1. So now this graph kind of does the opposite. So it's going to be reflected across the y-axis. So now it kind of runs the other direction and snakes down. Oops, and snakes down and runs off in this direction. So it kind of does that snake there. So that'd be the rough sketch of the graph going in the other direction. So one last example. The graph of the function is illustrated below. Treat it like a parent function and graph the following function. So what they want to do is graph this, but this down here is my parent function. So this is going to be my f of x function. So identifying the order pairs of my parent function, that they're already given to us. There's this -4, this -2. There's this -2 and this -2. There's this 2 and this 2, and there's this 4 and there's this -2. So when I graph this function, I have this -4, -2, -2, -2, 2, 2, and 4, -2. So remember the graph, if we use a light color, this graph kind of does across here, it goes up and crosses back down to there. So that's kind of our function. So we just brought it over to the graph. Now h of x, we have a couple things going on. So h of x, notice how we have this +1 on the inside. That +1 on the inside means I have a left shift. So my x values have to be subtracted by 1. And also have this -2 on the outside. That's going to affect the y's. And remember, the y's are just normal. That's just going to be losing 2 on the y values. So the -4, I have to lose 1. That's going to make that a -5. The -2, I have to lose 1. That's going to make a -3. The 2 lose 1 makes a 1. And a 4 lose 1 makes a 3. On the y values, I have this -2 lose 2. That gives me a -4. We have a -2 lose 2. That makes a -4. We have a 2 lose 2. That's going to be a 0. And we have a 4 lose 2. That's going to be a 2. So my new order pairs are going to be -5, -4, -3, -4, and 1, 0, and 3, 2. Actually, I did that last wrong, didn't I? That looks a little wonky. That wasn't the right value there. So let me get this going again. So we actually had a -2 over here is my y value. So -2 lose 2 should have been not a 2, but that should have been a -4. That makes better sense and things. Sometimes you just got to make sure this all plays out right. Careless mistakes happen all the time. So I should have a 3, -4. Let's see if that will create the graph that I'm looking for. So I have -5, -4, -5, -4 would be here. -3, -4, 1, 0, 1, 0, and we have 3, -4. So I should have the same graph, except it's just been shifted. So I've kind of follow those across. Let's see if I can kind of get that down there. So notice how the graph really looks the same. It's just been shifted to the left 1 and down 2. So it looks pretty good considering. So that kind of completes this lesson. Hopefully that's helpful, and best of luck on your work.